So, I'm Scott Crosby at Rice University. This is my research into done during my postdoc on Google Wave, on its security. So I decided to look at the authentication the Google Wave uses for cryptography. So, Google Wave uses a lot of crypto, and generally speaking, three of the major goals of cryptography are authentication. Figure out who created a given message. A second goal of cryptography is integrity. Do all detected messages are corrupted or altered? The third reason for cryptography is confidentiality. And I did a benchmark for based on the Fed1 text clients, which just basically inserted blips into waves continuously, and I got about in that benchmark showed that it was spending about 80% of the runtime was spent on cryptography, in particular RSA signing. And that's because RSA signing is about 10 milliseconds of signature. So there's a few solutions to this problem. One is you could consider using DSA. DSA signatures are about 10 times faster. You can also consider hash tree-based designs, which can offer throughputs much, much higher. And for verifying, of course, is a trade-off. Faster signing, slower verification. Slower signing, faster verification. RSA can verify about 3,500 messages per second. And another one is my research topic called spliced signatures. So in this talk, I'm going to focus on reducing the crypto costs by both appropriate choice of cryptography primitives and also aspects of the system design. And the goal is to create a primitive that's semantically identical to sign each message one at a time individually. I don't want to add any new interesting semantics by design. So why is OpenSSL not a good solution for this? It's fast, well implemented, and widespread. And OpenSSL is also very cheap. Once you initiate a session, you're just paying basically cryptographic hash costs and encryption costs, which have extremely high throughputs, and of course framing overheads. And OpenSSL is good and is used in Google Wave, but it offers primarily confidentiality. No one can read the XMPP communication. It also offers integrity. You can detect if it gets corrupted. And of course, SSL certs also serve an extremely valuable purpose. They bind a public key to a domain name. So you can tell who is the actual public key for wave.google.com. So one of the problems with OpenSSL is it doesn't really give authentication in a useful fashion in a federated system like Google Wave, because the sender of a message, the source of a message, isn't actually the author of the message. For example, if I'm the author of a message or an update that gets into the remote home server for some wave and then gets redistributed to a client, those clients receive the message from the home server, not me. So therefore, and you want to prevent a corrupt, broken, or otherwise rooted home server from forging messages under my identity. And other issues are, for example, that OpenSSL only authenticates the endpoint of the communication, which means you can't actually cache the information. You can't usefully cache the signature along with the actual message in question. And two, so therefore, Wave when authenticating messages for signing, there's lots and lots of signatures. Roughly each wavelet operation has to be signed when it gets sent. And for verifying, nominally each reader has to verify each wavelet op. So if a wave has 10 readers on different servers, that could potentially mean 10 verifications for each operation. So therefore verifying is at least as frequent as signing and possibly much more frequent. And crypto is slow. Here are some benchmarks taken on Java using one CPU core of a Core i7 machine in terms of the rate per second. Now Fed1, if you disable the cryptography, gets about 300 messages per CPU second. But using the current RSA 2048-bit signatures, performance is a lot lower, I believe around 80 or so per second. And this is why 80% of the time is spent on the crypto. Now the first optimization you can consider is well-known Merkle trees from about 30 years ago. That is, you amortize one expensive signature over many messages. And in this case, I use SHA-256 hash operations. They're about I need about 10 to 20 of them at about a microsecond each to do this. So a Merkle tree starts off with all the messages in the leaves of a tree. Here's an example with 7 messages. Then you create interior nodes in the tree where the hash of an interior node is the hash and the concatenation of the hashes of its children. So the first node on the left is the hash of the concatenation of the hashes of the messages x1 and x2, and so forth. And of course, you can add additional layers up to the tree, creating a root. If you take that root and you then proceed to sign it, here the box represents the signature over the root hash value, not that does not actually contain the hash value. Then of course, this signature can authenticate all the messages in the tree. Now, if you want to actually authenticate a specific message, it's actually pretty cheap. You just have to send, in this case, 4 separate hashes. Because from these hashes, I can infer up the tree what the root should be. Here's, of course, the implicit parts of the tree that aren't sent. And I can then check, is the reconstructed root hash equal to the hash that was signed? If the signature matches, then the dark green nodes, combined with verifying the root hash, can authenticate that one message right there. And I only have to send, in this case, 4 hashes, or about 128 bytes. And Merkle trees are insanely fast. So the actual Merkle tree itself is about 20 microseconds a message to act. That's the amortized cost of, if you have between 10 and 10,000 messages. It costs to build the tree and also to build and serialize the proofs for each one. That's from basically a list of blobs to a list of signature blobs, all serialized. And here I serialize one tree for each leaf. So if I have 10,000 messages, put them in a Merkle tree, or 10,000 byte arrays, put them in a Merkle tree and then generate 10,000 byte arrays of serialized protocol buffers. For each of the 10,000 distinct messages is, in this case, about 200 milliseconds. You would never actually use trees this big. So to actually use this, you need a synchronous signing API. And here's an example of one such API. Is you have an outgoing message, and you have a signature callback that's called with the byte array. And of course, you can also request for where the message bytes to be signed. Now, I actually have in my implementation code, I actually pass back a protocol buffer builder objects. Because the idea is that within my code base that I designed to be integrated with Google Wave, I take the protocol buffer, I put in the appropriate fields for the Merkle tree information. That gets called back, and then the part that signs each message individually using a certificate adds in, sets its own necessary fields. And then, of course, it serializes it via the normal processing flow. And of course, since I'm not signing messages one at a time, I have to sign a batch. I have basically a sign queue where I just submit a message to the queue. And whenever I want to, I call the run method, which basically builds the Merkle tree and processes everything. So I actually benchmarked this on the new API using, this is including the public key signature with RSA or DSA. And one CPU core can process over 30,000 messages per second potentially. And you can also choose the CPU utilization. And the idea is that if messages arrive faster, the trees get larger. If messages arrive slower, the trees get smaller, if you run the queue as fast as possible. And you can do that to minimize the latency. Alternatively, if you have a latency demand that's lower, you can run on a slower schedule. For example, run every 10 milliseconds. In which case, the CPU usage remains approximately the same. Sorry. If you run DSA at 10 milliseconds, CPU usage will drop significantly and latency will increase. Because cryptographic hashes are much fast. In practice, at reasonable message rates at a few thousand per second, almost all your time is actually spent on the RSA signatures. So you have inherent overload resistance if messages arrive fast or unexpectedly fast. The next part is how do you optimize verification? Verification's a lot harder to optimize because in practice, if the user sends consecutive messages on a wave, because of latency, they'll probably be in different batches, which means that the number of public keys that a federated server has to verify is roughly equal to the number of messages that are sent on the wave. Now this isn't quite true. A large-scale provider, like a Google-scale provider for federation, might happen to receive many messages from the same batch, on the same from the same batch, and it could receive a large-scale provider like Google could happen to receive messages sent from different users on different waves, which happen to occur in the same batch and not re-verify the root public key signature multiple times. But for a smaller scale provider, roughly the number of public key verifies equals the number of messages sent to that federated provider. And what that means is I'm limited to the throughput of standard public key crypto algorithms, which is 3,700 messages per second with RSA, or about 580 per second with DSA. But you don't actually have to verify all the messages immediately in many situations. For example, you want to verify asynchronously. For example, the users of a wave, some of the participants on a wave may in fact be offline, in which case you could, in principle, avoid verifying their signatures until the user actually logs in. Then you verify all the queued up messages that were targeted to them. Or a user might be, for example, read-only. It might be just reading a wave but not actually actively modifying it, in which case you might be willing to accept a few seconds of latency in return for reducing crypto overheads. And finally, of course, if a participant is just added to a wave on a new federated server, it has to catch up on all the old messages. In which case you really want a batch operation saying validate every message in the entire history since the beginning. In certain cases, we want a synchronous verifying API, something along these lines right here. We have an incoming message and a couple of get the signature, get the bytes, get the data bytes, and a callback that gets called when it gets verified. Now, when you're verifying it, you of course can submit an incoming message saying, here's a message right here. And we also want to force an incoming message. This means basically I need to know if this message is valid right now. Or you can also force everything in the queue. The reason why you do this right here is if you want to exploit delayed messages, you need to indicate when a message has to be verified immediately. In other words, you want to let it sit around because a technique I'll get to in a second called Spliced signatures can amortize one public key verification over several messages. And there's actually a lot of locality in the messages for Google Wave. So here I received from Google interarrival times for Wave messages. So here what I do is I basically look at, for a user on a specific wave, what fraction of the messages were sent with an arrival time less than the threshold. So this is saying that 55% of the messages a user sends on a wave are less than 1 second from the preceding message on that wave. And of course the hit rate goes up to 98% at 20 seconds. So if you're if you're doing a catch-up, if you could somehow exploit the asynchronous verification, you could potentially reduce a large number of signature verifications by a rather large margin in many of these scenarios. For example, a logged off user, when they log in, you might be able to save 98% of the signature verifications if they're the only participant on that wave on that server. So what a spliced signature is a way of amortizing one public key verification over a sequence of messages. So I assume I have a stream of messages. I have the cooperation of the signer. The signer has to explicitly include splice points in each signature. Splice is also transitive, and splice is also transitive. I'll show an example on the next slide. And this is the subject of a research paper that will be going out in about a week and a half. So here's the use cases. Let's say Alice publishes to some wave 3 messages, A, B, and C, each which includes a splice to the preceding message. At this point, Bob, a user on that wave on a different federated server, logs in. At that point, he wants to verify and catch up on all the preceding messages. What Bob can do is, Bob, instead of verifying the signature on A, B, and C individually, it could do that, but it can notice that these splices exist and can be connected together. So Bob can, so at this point, Bob will force the message basically A, and will implicitly get this case, Bob can force the message C, verify the one public key signature on C, and then get all 3 messages basically for free with one public key verification using very cheap hash operations. There's a lot of bookkeeping to track all the partial dependencies of all the splices in implementation terms. But this is the principle of it is that if you want to force a particular message, you figure out, you do one public key verification, and you potentially get one or many other messages for free with no public key verifications at all. So the benefits of this was done on a trace of 9 million messages derived from Google Wave data. Here I actually modeled the situation where I actually inferred log on and log off times for users. So if a user was online, then they wanted 0 latency. If they were offline, I was allowed to queue up messages until they became online. So in this scenario right here, roughly half the messages were forced, meaning I had to have them verified immediately. The other half I was able to delay verification. However, I performed fewer RSA verifications. This is because as many times our system was overloaded faster than I could do RSA verifications. 22% of the time. In these cases right here, I was unable to verify RSA messages as fast. I was unable to verify messages that were needed to be verified now as fast as they were arriving. So they got buffered up, and I was able to, with one verification, get several of these messages at once. So even despite being overloaded 22% of the time, I had latency less than 30 milliseconds, 99.5% of them. And worst case was only a couple hundred milliseconds, despite being overloaded far faster. This was including all the bookkeeping overhead as far as the signature module goes. Now, protocol changes to incorporate this into, for example, the Fed1 protocol designs. We need a more forward compelled representation of what assigned wavelet delta is. It's because you need to support, for example, individually assigned messages as is now, possibly the Merkle tree approach, or spliced signatures if you decide to use them. Also possibly handle RSA or DSA signatures. Finally, there's a new cryptographic hash being worked on right now, which will become the future SHA-3. Just as AES was produced the result of a contest in between 2000 and 2002, there's a currently ongoing contest to replace SHA-1 and the SHA-2 family of hash functions. So you need to be able to handle the future migration to SHA-3. I have a design, and we may bring it up in the protocol discussion later today. So basically, I looked at ways. So here's the possible solutions for reducing crypto overheads in Fed1, which could lead to the various performance improvements in the underlying code base. First is you could disable crypto if the server is local only. DSA signatures give you some scalability at a fairly cheap cost. This would be if you could get and use DSA certificates for assigning individual wavelet deltas, because DSA is about 10 times faster to sign. 3 times slower to verify, but 10 times faster to sign, at about 1,000 signs and 1,000 verifies per second. And at least from my benchmarks in applying Amdahl's law, I would estimate that would improve the Fed1 throughput by about a factor of 5 using one CPU core. Other choices with more implementation complexity to be RSA with Merkle trays, or these implementation terms much more complicated splice signatures. Now, they don't have to be as complicated as you can verify them without actually using the splices, because splice signatures, the splices may be used, but they don't have to be used. You can always verify each message one at a time, in which case it's a little more complexity than doing Merkle trees. So the code status I have is right here is the underlying code for the cryptography. Building all the prune trees and serializing them is completely unit tested. The queue for managing the asynchronous APIs I described is somewhat more immature. And the spliced signatures, all the bookkeeping to track all the splices is the least mature code base. We don't need to do, but that doesn't have to be. Spliced signatures can still be used without having a code activated. Questions? Yes?
On your experiment, were you running all this through Fed1?
No. I was hoping to, but I didn't understand the Fed1 code base enough to actually integrate in with the crypto backends.
So you're just generating the XMPP traffic?
I was actually running a separate program. I basically generated a program that would, I generated the queue, stuff which operated the queuing, the asynchronous API I described. Then set a traffic generator which submitted messages to that, following the Google Wave trace data. So it submitted information into the queue saying, message arrive. And then it requested, okay, user just logged in, now force all the following messages.
What did your Merkle tree, like, so with Merkle trees, you just, every time you send a Merkle tree, it was,
with
Merkle tree, sorry.
Yeah.
It was a list of hashes
No.
and a signature of the entire tree.
No,
and then what it cached if it saw that signature again, or the root hash, or the hash which was the root of the tree, so it didn't need to resign.
well, no. So what was the question?
Well, I'm trying to figure out how it would actually be implemented in Fed1. So, if let's say one federating server sends a whole bunch of ops to another federating server, then does each op individually say, I'm sending you this element in the tree, also here are a bunch of other hashes?
Well, no. Each op, I'm preserving the semantics of, I have a data block, a byte array coming in and a byte array coming out.
Yeah.
The outgoing byte array consists of basically the green things you see, the 4 green hashes,
Yep.
along with using this current Fed1 certificate to sign the hash of the root. So it consists of the current signature size plus 4 hashes plus a few bytes of protocol buffer overhead.
Yeah.
That's, each one is independent and separately sets.
Okay. But on the other side, the server which is verifying will it'll cache the hash of the root element, and that way if it sees another element which is in that same tree again, it won't need to resign.
It could, however, in practice, I expect trees would be relatively small. For example, 20 might be as few as 20 elements.
Yeah.
Because if you're running an RSA is the slowest algorithm.
Yeah.
And it can still run in this code base right here about 80 times a second, which means it's at 20 elements per tree. You're talking about a throughput of 1,600 messages per second, which is 5 times faster than the 1 CPU throughput of Fed1 in the benchmark that I did.
Yeah.
In which case, if you happen to encounter 2 in the same tree, you could apply the optimization. And you can ask, if you're Google scale, first of all, is it worthwhile even to detect that duplication efforts? If you're not Google scale, you might have, your odds of even getting too much in the same tree is pretty low.
Yeah.
And if you are Google scale, is it worthwhile detecting it?
Right. Yeah. Do you also incur the overhead of waiting until you have that many messages before you send any of them to Federation?
In practice, since the time to actually build the tree is so small, in 1 millisecond I can build a tree of 20 nodes. So I do an RSA loop, it's 10 milliseconds to do the signature, which you have to pay no matter what.
Yeah.
And then 1 millisecond lets you add 20 things onto the tree. So you're adding 1 millisecond onto the latency in return for about an 18 times increase in the throughput.
Okay.
So you are adding latency with such a small amount relative to the signature size.
Yeah.
That it's the optimization is almost, in terms of latency, almost free.
Yeah. Cool.
I do have latency graphs for I will have for the figure. I don't have them in the presentation, but generally speaking, at up to 20 or 30,000 per second, latency is about 2 or 3 signatures.
Yeah.
So you're talking 30 milliseconds. Pretty much 99% of the time less than 30 milliseconds.
Okay.
And with DSA, less than 10 milliseconds.
Yeah. Cool.
Yes?
Since there's a problem if the remote host is offline currently for some reason, what do you do if he never comes back? So he's sending deltas, and then he vanishes and never comes back. So you will never be able to complete all the signatures and verify it.
No, sorry. Do you mean the case of the spliced signature example? Yes. Or do you, okay. Then in this case right here, what actually happened, a spliced signature I think it remembers. Oh, sorry. If you remember the Merkle I just had right there, a splice signature includes additional paths, additional leaves. So this is included as part of the signature atomically. So a splice signature right here, this would include about a dozen or so more, 10 to 20 more hashes than just a straight Merkle tree signature would include. And they can be verified independently of any remote server. So given just these 3 blobs and no other information whatsoever, I can do the verification. Because these includes this additional information. And that makes it independence of any future contact with the server. So you have the public key you can use to verify that individual message. And you have the auxiliary information, independent from the server, to link it with a prior message. And if it links to a prior message which you don't have, well, you just ignore it. Or if, for example, say this message never arrived at all. Say Bob, pretend B didn't exist. Here I include C goes to splice to B I don't have, in which case I have to verify both A signature and C signature. And this the hashes for this splice point would be overhead that I pay but get nothing for. However, in practice, you can generate, in the case of Wave, you can generate useful splices. If, for example, Alice is sending 3 messages in a wave, it can always include a splice to the previous message that Alice sent to the same wave. That's an obvious, because then you know that that means that the reader is going to want to verify all 3 messages. And so you can be sure that splice has at least some minimal usefulness. Bob is willing to take, Bob's server is willing to take the latency hits, either voluntarily or involuntarily through overload. In my example, I overloaded very often in my trace simulation. And so thus Bob was forced to use splices, even though Bob wanted to verify my message immediately, so as I had to verify the public key signature immediately. I was in overload, I wasn't able to keep up.
It's a breakout, and then we have print it after the break, so technically we're supposed to start.